We are coming soon to orthogonal projection. First, decomposition theorem, orthogonal decomposition theorem. W is a subspace of Rn. For any u in Rn, we can find a unique vector W in W and the vector Z in W perp, so that U is the sum of the two. So here's the Rn. This is W, this is W perp, and this is the U vector, arbitrary U vector in Rn. The theorem says we can always write it as the sum of a vector. W is in W and the Z is in W perp, and U is the sum of W and Z. The proof is a construction proof. Suppose we have a orthonormal basis for W, V1 to Vk, and W is given by this vector. W is this vector, is a linear combination of this V1 to Vk vectors because W is a vector in W, right? So it's a linear combination of V1 to Vk, and the linear combination coefficient is, for the coefficient of V1, it's the dot product of U and V1, and for the second is U and V2, and all the last one, U and Vk. Of course, W is in W, and now the claim is this one. Suppose we let Z to be U minus W. Then we claim that Z is in W perp. So if we let W to be this vector, then we claim that the difference, U minus W, is in W perp. So let us see if Z is indeed in W perp. Z is in W perp if and only if Z is in B perp, because this is basis. This is the basis. To show that this is true, we can form the dot product of Z and vectors in B, Vi transpose Z, and let's see if the dot product is equal to 0. We substitute in the expression of Z is equal to U minus W, and here's W, so we throw in the expression of W here. And these Vi vectors are orthonormal, so Vi, the product of Vi and all these terms, V1 to Vk term, will be 0 unless it's except for the Vi term. And so for the Vi term, we get Vi transpose and Vi, and the Vi vectors are orthonormal, they are unit vector. So Vi transpose Vi is equal to 1, and then we get the product of V and U, the product of V and U, and a 0. So Z is orthogonal to all the Vi vectors. So indeed, this is true, and this is true. U is a sum of W plus Z, where W is in the vector is in the subspace of W, and Z is in W perp. So far we have shown that indeed U is a sum like this. We still need to show uniqueness of W and Z. Say U can be expressed as W prime and Z prime, and this W prime is in W and Z prime is in W perp. Then we get W plus Z same as W prime plus Z prime. Moving W prime to the other side and Z to this side, this is what we get. And what is this vector? This is W minus W prime. Both of these two vectors are in W, so this is a vector in W. And both these vectors are in W perp, and W perp is a subspace, so this is vectors is also in W perp. So we have this vector in W and also in W perp. And that means this vector is equal to the 0 vector. So W and Z are indeed unique. This W vector, the unique W vector, is called the orthogonal projection of U on the subspace W. And it's given by the expression that we had earlier. But we can rewrite it a little bit. This is a linear combination of the V vector, so we can write it as a matrix vector product, V1 to Vk, and these are the linear combination coefficients. And in this vector, we observe that every one of these terms has a U. V1 transpose U, V2 transpose U, and VK transpose U. So we can pull out this U, the same as above, and we also have this V1 transpose V, to VK transpose, and then U. If we call this matrix B, the dimension of B is M by K, then this one is B transpose. So the orthogonal projection of U on the subspace W can be computed in this way. If we have the U vector here, and if we have a orthonormal basis for W, we can use the basis vector to form a matrix B. Then the orthogonal projection vector W is BB transpose U. Let's define the function based on orthogonal projection. W is a subspace of Rn, and the function UW, this UW, W is a subspace, is the subspace that we have here. So this is a function, and the subscript is a subspace. This function from Rn to Rn is defined as the image of U is equal to W, where W is the orthogonal projection of U on the subspace W. A question: is this function UW a linear function? Remember how orthogonal projection is related to U vector? So is UW linear? It's indeed linear, isn't it? Because the orthogonal projection vector, the image of U under UW is equal to BB transpose U. So indeed, this is linear. If it's linear, then it has a standard matrix. What is the standard matrix? PW. Again, this notation, P matrix PW, it has a subscript, and this subscript is the subspace W. The standard matrix of UW, let it be PW. What is PW? It would be BB transpose. This UW linear function is called the orthogonal projection operator on W. And its standard matrix is called the orthogonal projection matrix of W. In our earlier discussion, we have found that PW is equal to BB transpose. And this B, whose column vectors form an orthonormal basis for W. So if we want to compute this orthogonal projection matrix, we need an orthonormal basis to start with. The following theorem shows that we can find PW starting from a basis, just a basis. It doesn't have to be an orthonormal basis. From an arbitrary basis for W, we can obtain the orthogonal projection matrix. Suppose we have a subspace W over Rn, and a matrix C is an M by K matrix whose columns form a basis for W. Then Theorem 6.8 says that starting from C, we can compute the orthogonal projection matrix. It is given by this expression: C transpose C inverse, C transpose. Thus, C transpose C would be K by K, because C is M by K, and the C is M by K, and C transpose is K by N. So size-wise, this is how it goes. C is M by K. It's a narrow, a tall matrix, and C transpose is C inverse. This is a square matrix, and C transpose is again K by N, so it's a wide matrix. To show this theorem, we will first show a lemma which says that this C transpose C matrix is always invertible. C be an M by K matrix with the linearly independent columns, then C transpose C is always invertible. We know the matrix is invertible if and only if the homogeneous equation has only the solution x equal to 0. So instead of showing that this is invertible, we can show this is true. The solution is unique. The homogeneous equation has only one solution. So let's consider the homogeneous equation. Let's multiply both sides by x transpose. Then what do we have on the left-hand side? This is x transpose, C transpose, and Cx. The first part is exactly the transpose of the second part. So this is Cx transpose Cx equal to 0. This means Cx norm square is equal to 0. So Cx is the 0 vector. But we also know that C has a linearly independent column, so the solution is the 0 vector. Now that we know this is C transpose C is invertible, we can start on the proof of this theorem. Let's consider the QR factorization of C. C equal to QR. Remember, C has a linearly independent column. So we can write down this QR factorization where this Q matrix has orthonormal column vectors. So Q transpose Q is the identity matrix. Therefore, the columns of Q form an orthonormal basis for W. We know PW now can be written as QQ transpose. So let's rewrite Q in terms of C and R inverse by multiplying both sides by R inverse. So QQ transpose becomes this expression after we substituting Q by this. And this is a C R inverse R minus transpose, C transpose, and this is the same as a C, R transpose, R inverse, and C transpose. In the theorem, we have C transpose here, C transpose C, so let's try to see how C transpose C is related to everything else. If we write down C transpose C, and C is equal to QR, then we would get R transpose, Q transpose Q, and then R. And we know what Q transpose Q is. It's the identity matrix. So C transpose C is in fact equal to R transpose R. And now we can substituting R transpose R by C transpose C here. Then we get PW in this expression, and that's what we want to show in the theorem. Let's look at an example. W is this subspace, is the collection of all the vectors that satisfy this equation, and that in fact corresponds to a null space. And we would like to find the orthogonal projection of this U vector. This is U vector. To find PW, we can either have an orthonormal basis, and in that case it will be easier. PW will simply be BB transpose, or if we have a basis, just a basis, not necessarily an orthonormal basis, then we can use the theorem that we just saw to find the PW. And this W subspace is actually a null space, so we can find a basis for W easily. W corresponds to the null space of this matrix 1, minus 1, and then 2, x equal to 0. It's the null space of this homogeneous equation. This is a scale of 0. So if we write down so now we can write down the general solution for the vectors in the null space. V is equal to x2, 1, 1, 0, plus x3 minus 2, 0, 1. Let's call this C1, and this is C2 vector. Then we have a basis. C, that C be C1, C2. Then W is the column space of this C matrix. The two columns vectors of C matrix form a basis for W. So PW is C transpose C inverse, C transpose. Plug in the matrix C here. So this is a C transpose C inverse, C transpose, and we get this matrix. The product is this matrix PW. Having obtained the orthogonal projection matrix, it becomes very easy to compute the orthogonal projection of an arbitrary vector U as the matrix vector product PWU. Throw in this matrix PW and the U vector, we get the matrix vector product result 0, 4, 2. At the end of 6.5, we come to the question that we posed at the beginning. Given a subspace W for Rn and an vector in Rn, an arbitrary vector in Rn, what is the vector in W that is closest to U? And the answer is the orthogonal projection of U on W. Let's see why this is true. For an arbitrary vector U in Rn, we can write it as W plus Z, where W is in W and Z is in W perp. And suppose V is a vector, an arbitrary vector in W. Now let's compute the distance of U and V. This U is this vector U, and V is an arbitrary vector in W. We want to compute the distance between U and an arbitrary vector V in W and see what it is. U, we can write it as W plus Z, and let's rearrange this. We have Z here, and then W minus V, and let's work it out. This is Z norm square, and this vector norm square plus 2Z transpose W minus Z minus V. Let's take a close look at this dot product. This z vector, we know it's in W perp. How about this W minus V vector? W is a vector in W, and V is an arbitrary vector in W. So this is V, and their difference is in W because W is a subspace. So this vector is in W and this vector is in W perp. So what do we have? This dot product would be 0. So this is the distance would be the distance of Z norm square. The distance square will be the norm square of Z plus the distance between W and V square. Now U is a vector that's given to us. So from U we can compute W and we can compute Z. So Z is also a vector that is already determined once U is given. Only this V is an arbitrary vector in W. So this norm square plus this norm square is larger or equal to Z square, Z norm square. And we see that the distance between U and the arbitrary vector in W is at least this much. And when does equality hold? Equality holds if and only if this is the zero vector. If and only if V is the same as W. So by choosing V to be equal to W, we can achieve the smallest quantity. We can achieve the minimum. So the shortest distance between U and a vector in W would be Z norm square. And the smallest distance is achieved when this vector is the orthogonal projection of U on W. And this is how we define the distance from a vector U to a subspace W. It's the distance between U and the orthogonal projection of U on W. The result that we have here, the distance between U and V square is equal to the norm square of Z plus the distance square between W and V. This can be interpreted using Pythagorean theorem. Suppose we have the subspace of W here, and this is a U vector, and the orthogonal projection of U vector on W is this W vector. And this is the Z vector. V is another vector on W. This is V. And this is the distance between U and V. This would be U minus V. And the distance square is equal to the length square of Z plus the distance between W and Z square. This Z would also be orthogonal to the difference vector W minus V.